In this video we're going to show you how to restore if you want, the Collins MP1 mobile power supply. We have another video that goes more into detail about what this power supply is, what it's used for, what it was developed for. This video focuses on the modification of it, the retrofitting. The only thing I want to say about it is it generates high voltages for tube equipment. It takes 12.5 volts input, 13.8 if you want, and it generates 260 volts DC, 800 volts DC, and an optional 130 volts DC. And it did that for equipment like the KWM1, the KWM2 or 2A, but like I said, it can be used for other tube equipment as well if you want to use that mobile from a car battery. Let's open it up as a start, and I'll show you what we need to do to modify this. Alright, I took off the screws on the corners of this housing, this cover, and here we see the insides. The insides is an aluminum frame. Underneath there is a power transformer, the on-off relay, a couple of chokes, and the PCB that's screwed into the frame contains the high voltage capacitors for the 800 volt. These are the two filter capacitors for the 260 volts. Here is the capacitor bank for the minus 65 volts negative. That also is being supplied by this power supply for the grid bias for the power amplifier, and that is adjusted with this potentiometer to the proper bias current for the PA. And again, underneath here you can see more. We see the actual transistors there. There is 2 germanium transistors. There is more chokes, and we have a bypass capacitor there, and the big resistor there. The resistor bank that we have here is used for biasing the germanium power transistors. Now what we got to do is remove this board so that we can replace that with a new board. The new board, we sell that as a kit, already soldered obviously, because there is SMT components on there, and we didn't want to do that to you, so we have it already pre-soldered. The only thing that needs to happen is old board needs to be removed, new one needs to be put in, and the only thing you need to reuse is this potentiometer that goes here, and we will go into detail once we get to that point. As you can see, the actual power supply is again having these 6 800 volt capacitors, 3 in series, 3 in series. These are the 2 capacitors for the 260 volts. This is the bypass capacitor that you saw there. And these 3 are the 3 for the grid bias. And those were the ones that you saw here. Now, the power transistors, believe it or not, are actually on this board. These are power MOSFETs. And they have such a low on resistance that they don't need any heat sinking. So that's the big advantage of this modification, this retrofit if you want. The transistors, the MOSFETs that are used, the switching MOSFETs, do not require heat sinking, and as a result the efficiency of your modified power supply will be much better and there will be less heat developed. The MOSFETs are driven by a microprocessor circuit, and as a result the switching frequency is always constant. We don't have that variable like in the original situation. The original situation, it depended on the load what the frequency would be. It's anywhere between 800 and 950 Hertz. This one runs at a continuous 1600 Hertz. You will think, why 1600? That is because the transformer has the highest magnetic efficiency there. As I told you, the power supply has an option for a 130 volt circuit. That was basically there also in the original concept, Collins concept, but it was not implemented on this board. there is no room for a 130 volt output. And the 130 volt output, you can see here, Collins basically has this dotted diagram. That is the additional circuitry that would be needed. And like I said, on our board we have that as an option. And we can put it on there when you order the board as an option. If you need that, it's an additional $10. And it is in compliance with the actual Collins design. Now you can see how this is set up. You got power germanium transistors. This is the biasing circuit I told you about. These are the chokes. More chokes here. This is the high voltage rectifier. This is the low voltage, if you want, 260 volt low voltage. And this here is the negative bias voltage, which has a single phase rectifier. And we kept this the same. This circuit has been completely redesigned. And you can see that here. This is the new circuit with switching MOSFETs. These are MOSFET drivers. This is a microprocessor power supply for the CPU, and of course we got the filtering. And here we didn't change too much. The concept is basically the same. The only thing is we added a bleeder here to make sure that the 260 volt also bleeds off when you turn off the unit. The original Collins design didn't have that. The negative bias rectifier, we kept it identical to the old concept. So let's start with getting rid of the old board and putting in the new one. Now the first thing that you'll have to do is detach the wiring here, which is connected to this terminal strip that you see here. There is 5 connections there. I think this is the 800 volt. This is the output for the 13.56, 13.8, sorry, that just passed through from the relay. That is for the tube filaments. This is the on-off signal for the relay. So this is how you power the relay, by pulling this to ground. This is the 260 volt output, and this is the minus 60 volt output. These jumpers here are to switch the unit over from positive to negative ground and back. It's right now set up for negative ground. That is going to be an important thing to focus on the modification. I'll show you that later. So the powering, basically, this is the plus 13.6, and this is the ground, the minus. It needs pretty hefty DC cabling. So the first thing I would like to do is to remove these so that you have better access to these solder points that you have to solder to take off the wiring. So we might as well just cut them out, because we're not, like I said, we're not going to use this anymore. You just use a wire cutter and cut these things out so you have better access to here. Before we do that, I wanted to show you something else. There is an older and a newer model. It's an early model and a late model. This is another MP1, but this is the late model. And the difference resides in these 2 chokes here. There is 2 chokes mounted on the chassis here. And in the later model, those have been omitted and replaced by this choke here. That's the filters, RF filters, the 260 volt output, and a resistor in the 800 volt buffer network. And that you can see here. This is the choke that I was talking about here. This is the high voltage choke, and in the schematic diagram that has been replaced already by a 33 ohm resistor. So that's important. That changes the things a little bit for the modification, but I'll show you both situations. Now the new board, you could, for both the old and the new, the early and the late model design, you could just use the same board. As you can see, this is the inductor that we put on the board already for this filter inductor here. Did I say this one? That's wrong. It's this one. This is the RF filter on the output of the 260 volts. And the 33 ohm we have here. So you could just remove these two if you don't want them anymore. Or you can leave them, and then you basically don't need this inductor and you don't need that resistor. And the board has facilities to connect the wiring for that high voltage inductor. You see, if you cut out that resistor, then you get access to these terminals here, and that is what you would solder to the high voltage choke over there. So there is a slight difference, and I'll modify both of them, both the old one and the new one, and that will give you a good idea how to deal with whatever you might have yourself. Like I said, I'm not going to just cut out these old electrolytic capacitors, so I have better access to their solder points there. Alright, I removed those capacitors just by cutting them out. Here they are. And they're all slimy. There is this sleeving material, I think it's soft PVC, that has been leaking softener chemicals. And as you can see, it actually corrodes the board. That's another reason why you cannot just change these caps and think the thing is going to be like new anymore. And here you can see the same thing in the other power supply. This corrodes the board, and that is a reason why you want to get rid of the board as well. But anyway, here you can see that the wires are mostly terminating onto the board here, but this thick 13.8 wire goes through a hole. It actually goes to the relay, and this is the control wire for the relay. It goes in the hole in the board. This is the output of the 260 volts. That also goes through a hole and actually connects to that inductor I was telling you about. So there's 3 wires that you would have to desolder from this terminal strip, and the other 2 go to the board itself. This is the 800 volt and this is the minus 90 volts, and those you might as well just desolder from the board, so there is no reason to desolder that from the terminal block unless you want to, of course. Now, and this is also where there is a slight difference with the newer design, the late model. The difference there is that the 260 volt terminal goes to the board. It doesn't go through a hole to an inductor, because that's not there, remember? It goes to this inductor here, which forms that function. So in the new design, in the late model design, you only have to desolder this yellow and this white wire from the terminal block, and the rest you can just desolder from the board itself. That is the only difference between the late model and the early model. Alright, I have now, for the early model, removed the brown wire from the board. I have removed the gray wire that goes to the hole here from the terminal. I have removed the yellow wire from the terminal that goes to this hole. I have removed the white wire that went to this one here. And the red one I have desoldered from the board. So there is 2 wires that I desoldered from the board and 3 wires that I desoldered from the terminal block. Now here in the new model, in the late model I should say, same thing. This was desoldered from the brown wire was desoldered from the board, but here the gray wire was also desoldered from the board because it went to this inductor, not to the hole. The yellow wire that is here, I have desoldered that from the terminal block, and the white wire for the 13.8 volts I also desoldered from the terminal block, and the 800 volt red wire was desoldered from the board. So the next step is to take out the 6 screws that hold the board down, and then desolder all the wires that are on the bottom of this board. There is a whole bunch of wires from basically that go to the transformer that need to also be removed from this board, of course, before we can take it out. And the new board was designed such that the whole configuration is the same for those transformer wires. Well, we'll get to that once we have removed this old board. And we do that for the early model and for the late model. Alright, the 6 screws are removed and the board is now loose. There is one thing I would like to mention to you. I had one problem when I unscrewed that particular screw over there. There is a PEM nut on the other side that is pressed into the frame. And since these things are screwed in there with Loctite, the PEM nut started to rotate and I couldn't get the screw out. If that happens to you, what you need to do is just heat up that screw with your soldering iron. Then the Loctite will become weak and then you will be able to unscrew it without a problem. So again, if the PEM nut starts to slip on the other end, then heat up the screw real good, and so that the Loctite gives out, and then you can just take it out. In any case, now I will show you what the next step is. Since all the wire connections are on that side, you can hinge the board up like that. And there you see the wiring that you need to desolder. It looks more complicated than it is, and again, you know, when we assemble the whole thing again, I will go over the wires and where they need to go. But the important thing now is that you just desolder all these wires one by one that are there in the connector row on that PCB board there, and then we can take it to the next step. Then we will be able to remove the board in its entirety and prepare the chassis for the new board. So just desolder all of that so that you can lift out the board. The wires will come through the holes, so that's not a problem. Once you have desoldered that, you should be able to lift the boards out and discard it. Alright, we have removed the original boards for both the early model and the late model. Now, to be honest with you, I didn't desolder because they were hard to pull out. I just cut them all, and that means we need to restrip these wires. They're long enough, so it's not a problem. So maybe it's better if you just cut them and then restrip the electrical wiring that you have here, and we'll do that. And I'll show you what is a good way to do that. Alright, I restripped and resoldered all these wires. That looks nice now. Now, I gotta warn you, these wires are hard to solder because they're 50-year-old and they've developed some oxide layer, even where it was protected by plastic. So you're not going to be able to solder it with standard rosin solder. So what I use is this water-soluble flux that is sold at Home Depot and Lowe's for not too much money, $5 or something. And that stuff gives a much better soldering strength. So if you use that for these wires, you should have no problem at all to solder it. Like I said, it's not expensive, it is not corrosive, and for tinning these wires, that should be the ideal solution. Don't use it on the electronic boards because it's slightly conductive, but for tinning these wires, it's the perfect stuff. The next step is to remove these old germanium transistors. It's the DA3F3 from Honeywell, and we're not going to need them anymore. So there is 2 thick wires to the emitter and the collector. There is 1 thinner wire that goes to the base, and the same is true on the other side. So what you got to do is remove them, and you can do that by loosening this nut here. They're stud mounted. Just cut the wires, don't solder them, it's not needed because you don't need the full length. We'll get to that later, but the transistors need to be removed. If you have trouble getting to the transistor here because of these components, well, these have to be removed too. Remember, these are the 2 bias resistors, and this is the bypass capacitor, and they all need to be removed. The only thing you got to do is cut them off short so that the wiring stays intact, and I'll explain you later why that's the case. Just take off these nuts. You might have to warm it up a bit because it's Loctite treated. And then cut off the wires close to the resistor, and then we'll explain you which wires to keep and which wires to discard. Alright, the resistors are removed, and now we are gonna remove the second transistor. Remember, just cut the wires as close as you can to the transistor, but don't cut the transistor legs itself, just cut them close to the transistor. Alright, as you can see, this is the feedback winding 5, 6 and 7, and none of these wires are needed anymore. These are the wires that are going to the base of these transistors. So that wire you can cut away. This wire that goes from pin 13 and 14 from the transformer is needed. So you need to leave that in place. And the 13 and 14 wire is here. I cut that. Remember, that was cut loose from the resistors. So leave that one in place. These 5, 6 and 7 wires, they can go. You don't need them anymore. You can either just cut them off here and leave the wires in the unit. I prefer to remove it altogether from this wiring harness, because you know the base wire terminates here for one transistor and here for the other transistor, which is much closer to the transformer, of course. But I would recommend to just remove them altogether. Then there is this stud here with wiring left. I would just remove this wire here. This is the T that goes to this big choke. This choke. And this T used to go to the emitter of these two big transistors. And the ends of that T will go to the PCB. So you need to leave this wire in place. And I would also leave this little wire in place, which goes to this isolated stud. There is two reasons for that. One, it gives a little bit of mechanical stability. The other one is you can use that later as a measurement point if you want to look at the waveform across the MOSFETs. So this is a nice reference point. So I would just leave that. But you do want to remove this wire, obviously. And like I said earlier, the wire that goes to pin 14 and 13 of the transformer, that needs to stay intact. You're going to have to connect that to the board later. And as you can see, I already removed the wiring from 5, 6 and 7. Right, so we have accomplished quite a lot. The transistors are removed, the excessive wiring is removed. We stripped the wires that need to be reconnected to the board. We'll get to that. This transistor is removed. This T-bar is freed. This wire will be reused. I removed the wiring and left this little stud in place. And now there is some things you want to do to prepare the chassis before you start mounting the board. These jumpers are going to have to be moved to the vertical position. That has to do with the fact that the original board used PNP transistors, but we are using N-channel MOSFETs in the new design. So for that, if you want negative ground, the jumpers need to be in this position, and for the old board they used to be in this position for negative ground, which is the way it's drawn here. So what we're going to do is remove these 4 nuts, take the jumpers off, and then we're going to retighten the nuts that are underneath there, because after 50 years you will notice that these nuts have loosened somewhat. And before we replace the jumpers in the vertical position, we're going to retighten all those nuts and do the same one for the hot terminal. This is the plus 12 volts. That terminal also might have come loose a bit. So we're going to take off the second nut and tighten the first one that holds it down to the chassis. The jumpers are in the vertical position, as you can see. Just one word of caution: when you tightened these nuts earlier, make sure that nothing rotated around, especially the ground wire. I noticed it is easy for that. You can see it very well, but it's easy for that lug to turn around with the risk that it might have shortened one of the other studs, one of the other screws. So be careful that when you tighten this, that nothing has rotated in the back to the point where it might cause a short. Actually, what I did is when you tighten the nuts, put a Phillips screwdriver in there, and to make sure that that doesn't rotate with it. That is really the best method to do the nut tightening. There is another thing that's important, and that has to do with this choke here, the one that you see here, which is this choke in the basically in the 250 volt filter network, buffer filter network, L3. The terminals need to be positioned such that they are parallel to the center line of the chassis. So that you want to parallel to the screwdriver. If you draw an imaginary line from left to right, then you want these terminals to be parallel. Now on the late model, which is what this is, remember there is no inductors here, that is not that big of a deal. But on the early model, I haven't removed all this stuff yet. On the early model, Collins made a screw up. You see, this is the early model with the chokes on the chassis. Collins screwed up at one point, and nobody's perfect. This older inductor in the early model is higher, and the terminals touch the board, which is not good, obviously. Now we have designed the new board such that there is two holes that facilitate some space for those terminals. But in order to have this line up with the holes on the new board, you need to rotate this a little bit, rotate this inductor, it's a toroid basically, such that this becomes parallel to that center line I was talking about. It's pretty easy, just loosen that screw, turn this thing to the point where that is the case, and then you should be okay once you mount the new board. You see, I've loosened the screws, now you can turn it around. The wiring is more than long enough. So place those, rotate this toroid to the point where these terminals are parallel to that center line I was talking about, and then you will have them positioned exactly above those, underneath those holes. Okay, so that's important so that you don't cause any shorts once we put on the new board. Alright, I have tightened the nut again. I turned this, rotated this in the right position to make the contacts parallel to that center line and imaginary center line I was talking about. Remember, that's only needed for the early model. Early model you can recognize on these two chokes. The late model used a much lower toroid inductor, and the terminals can never touch the PCB board no matter in what position they sit. So for the late model you don't have to do this particular rotating. For the early model you definitely will have to do that to make it line up with these holes on the new board. And don't, like I said, don't forget to tighten the screw afterwards. Alright, the old model we have now prepared as well. The transistors have been removed. The excessive wiring is removed. We left this wire here. This is the support wire for the T-bar, as we call it. The only difference between the old and the new model, the early and the late model, is that this one has an extra stud, the old one, where the new one did not have that. Only one. And the reason is, in the old model a stud was used for the network here, and the new one, that capacitor that resided here was soldered directly onto the resistors. I guess there was a cost reduction. So you can either remove it or leave it, it doesn't matter, you don't need it anymore. The other thing I found was that in the old model, the transistors, the nut was treated with Loctite, and I had a hard time loosening that. And again, the best way to do that is to heat this all up with either your solder iron or maybe a paint stripper. But if you heat this up, then you will have no problem loosening that nut. If you don't do that, it's impossible to get off. The same was actually true for these resistors. That also has been treated with Loctite, and you really need to make that hot. Otherwise, you won't be able to get that out. So that's another tip that I have for you. Everything that's treated with Loctite, heat it up before you start unscrewing it, because without heating it, it's an impossibility. The next step is to retrieve, to salvage this potentiometer from the old board. Since we're going to reuse that potentiometer on the new board. The best way to do that is to desolder these 3 points. I'm going to use the solder sucker for that, but there is obviously other ways of doing that. And then to loosen the nut. Now the problem that you already see here is we have lots of Loctite there. That makes it hard to loosen that nut without heating this up. I don't really want to make that potentiometer too hot. So I will use this this dentist tool to scratch that away, and to use some lacquer thinner to soften it up before I do that with the dentist tool. And then it should come off without a problem. Again, we're going to solder sucker these out, and then we're going to loosen that nut by using solvent and this dentist tool. That should make it happen. Okay, we got the potentiometers out of there. You see I left the original wiring intact because that will fit nicely on the new board. The same holes as on the old boards were designed for that. We got that loose, gone. Now it came off pretty easy with the lacquer thinner. I can recommend you this stuff. That went easier than I thought, so I wonder if that's actually real Loctite that Collins used, because I don't think that would dissolve that easily. It might be just some kind of transparent paint, but whatever it is, with lacquer thinner you should have no problem to get it off. And now we're going to mount these potentiometers onto the new board. Like I said, the new boards have will facilitate these holes and the hole itself, of course, the mounting hole. Okay, the potentiometers are in place and soldered. As you can see, perfect fit, using the original jumper wires that were on the potentiometers. And you should be ready to get to the next step. Before I'm going to put in the new board, I have to deal with this stuff here. This is the rubber that was, the rubber grommet, the ring that was used between the cover and the chassis. As you see, it has completely deteriorated after 60-70 years. So I gotta get that stuff off. It's gonna be a mess. Obviously, I'm not gonna let you participate in my suffering. So I'm going to do that, clean it, and then we'll go to the next step. You might have to do the same depending on how old your MP1 is or how it was stored. This, for instance, this one doesn't have it, at least not as bad. So we're going to do that now. Alright, that was cleaned. The next step is now to bend up these wires, the thick wires that go to the MOSFETs, such that they will more or less fit in the board before we solder. These are the emitter connectors, the source connectors, and this is where the drain goes. Drain goes to the transformer, remember, source goes to that T-bar. So we got to bend them up to the point where they more or less coincide with the holes that we already have on the board. Now on the late model, the bending up is not going to be that of a problem. The wiring is not in the way of anything else. But in the old model, in the early model, as we can see, the wiring for this choke is in the way. Now I could just loosen it, desolder it, but this thing is held down by a screw, so I think what I will do is just go down, remove that screw, and then I won't have any problem to make that wire. The two thick wires here pass this thin wiring, so there is no need to solder. I'm just gonna unscrew that choke and do it that way. So I band up the source and drain connections, and I cut away the insulation. The good news is there is no lacquer or anything on this. This is bare, well, it's copper, which seems to be silver plated. Same is true here and here, so I basically cut it off to the point where it's about equal with, where the insulation is about equal with these flanges, and then we should have no problem to put that later through the holes that are there in the board. M101, W101, W103, W102 and W104 are the holes I'm talking about. So I did disconnect the choke, and I'm gonna tighten that again, and then we go to the next step. Now, first thing you gotta do when you mount the board, or you place the board on there, is to put the thick 13.6 wire and a thin yellow control wire through this hole, and the gray wire that goes to this inductor here. That's this wire here. See it move? That wire goes to here. That is the 260 volt output, which will later go to terminal 4. Alright, so if you take those through the holes first, then they won't be in the way when you start to solder the bottom wires. So do that first, and then we go to the next step. Alright, this is the late model. Basically the same procedure. Strip these thick wires, so move them such that they can be put in the holes on the new board. And also, forgot to tell you that, don't forget to strip and to tin this wire here. That was the wire connected to 13 and 14. Once the new PCB is mounted on there, it will be much harder to strip this wire and tin it. So that is another thing you need to think of. I also noticed something else. I noticed this transformer is a little bit loose. You need to tighten that nut. Apparently after 50 years that has become a bit loose, so you might want to check that too. Make sure that transformer is bolted down properly. Alright, we're back to the early model again. First thing we're going to do is solder these two red wires. That's actually the 800 volt AC input to the buffer network, the filter network. And these are the brown wires. They go to that 800 volt choke that you see here. And discovered something that's a little bit of a problem. These wires are a little bit too short. They need to go in here. Can you see that? They need to go in here. And they're a little bit short. So what you got to do is cut this wire tie here, so that you have a little bit more slack there. So the board actually shows where the red wires go. You see that? T13 red and T14. That's terminal 1 on transformer 1 terminal 3, transformer 1 terminal 4. The TB1, TB stands for terminal block. So that is the red wire here. That goes to terminal block 1, contact 1. But we will do that at the end. Let's first solder the ones on the bottom. That is easier. And then we solder the ones on the top. So the two red wires that I showed you go to T13 and T14. And then the brown wires that were a little bit too short go to this one, and this one is normally where the resistor is. But you know, if you have the early model, then you have the choke here, and then you might as well put the choke there instead of the resistor. Now, if you wanted to get rid of that choke altogether, you can do that too. Then just leave the resistor in place, and you don't have to connect anything. That won't make a difference from an electrical standpoint, I've noticed. That's probably also the reason why Collins got rid of the choke. But if you really want to be strict, then you should solder the brown wires to those, and that's what we'll do in this case. Alright, the red wires are in place, as you can see. The next wire we're going to deal with is this black wire, the one that's close to the two red ones. And we increased the slack for the brown ones, but we'll solder those later, remember? So now we're going to this black wire here, and as you can see on the board, well, let me position it a bit better for you. On the board, that is right here, T1 transformer 1 terminal 8, and as you can see we have soldered the two red ones, and we're now going to T1-8, which is the black wire. Alright, as you can see the black wire is in place. We're now going to these two orange wires, which is the 260 volts AC. T1 transformer 1 terminal 2 and transformer 1 terminal 10. That is the two orange wires that you see here, and those will go there. Polarity is not important, just make sure it's the two orange ones that go there. As you see, the black one I already soldered in place. So now we're going to the two orange ones. Okay, the two orange ones are in place. The next one would be terminal block 1-4, so that would be terminal 4, but that's not used on the old model, remember, because this this choke here actually is located here, so this gray wire goes directly to terminal number 4 here. So for now we're going to leave that alone. Then we have to go to L3 pin 1. L3 pin 1, that is this toroid here, the 260 volt choke, and we want to have this particular wire. There is two wires soldered to this one. That terminal only has one wire, and that is the gray wire we want. The thing is, there is two gray wires here. There is two gray wires from this choke, so it's a little bit difficult, but you have to do this right. So the best way is to take your own meter and measure which wire is where. Like I said, we need this wire, which in my case is this wire. If you want to make sure, just take your own meter. There is about 45 ohms difference between these two pins here, so you should have no problem determining which one is which. And this is the one that we want, and we will solder that to L3-1. Alright, L3-1 is in place. Now we're going to transformer 1 terminal 9, which is a black wire, which is actually the return wire for the bias circuit. So that is this number 9 here, which goes to ground. So that would be this wire here, but there is also another black wire, so I will take my ohm meter and make sure that this goes to pin 9 of this transformer. So just take the black wire that goes to pin 9 of this transformer, and that needs to be right there. Now this transformer doesn't have any numbering, but on the schematic diagram you can see how the numbering is on the transformer, so keep that in mind. Pin 9 turns out to be right here. I think it's this one. So we're gonna check that and then make sure that we put that in that right hole there. Alright, so remember, this was number 9 for the black wire on the transformer, and that goes right there, and that is the T19 black here. Now the next one is E3 black. That's just the ground strap. E3 is actually this terminal there, so it's part of the jumper block. It's the ground part, and it's a little bit difficult to see with all this stuff here. Well, we see that black wire right here, and it goes to this ground terminal, and that goes to the hole I just showed you, which is E3 black. So that should be easy, but just to make sure that you take the right black, it is the one that really goes to the chassis ground, and we're going to solder that now. Okay, we got E3 black in place as well. That's where it went. Now we're gonna focus on the second terminal of choke L3. So this is the one here. Why isn't it focusing? Yeah, there we are. L3-2. That is a gray wire, and that is the second gray wire we still had left. And if you want to use the ohm meter, you can be sure it needs to be this one. That is terminal 2 for L3. And if you want to use your ohm meter, keep in mind there is about 45 ohms difference between these two. That's how you can distinguish between these two wires in case you got it wrong or something. But anyway, that goes to this position, and we're gonna solder that now. Alright, we got all these wires in place now. The bottom wires are all soldered in place. So the ones that are still open, that is basically the brown minus 65 volt wire that goes here. We have the red 800 volt that goes there. And like I said, we don't solder this one for the early model like we have here, because that choke is on the bottom, and this is the gray wire that goes to terminal 4 here, pin 4. So we still have the brown wires here as well. That goes to the high voltage choke, remember? But we'll solder that in place later when this board is mounted, because it's easy to reach from the side. We're going to focus now on those thick wires that go to the source and the drain for MOSFET 1. And here is the other one, drain and source for MOSFET 2. And we still have to solder our 12 volt supply wire that goes to the board. And I still need to strip it. You see that? It's better to do it now when the board is not in place yet, otherwise it's hard to read. So I still got to do that for this this power supply. And that actually goes to here. 12 volt it says. And that should take care of that. So we're going to do preparation for that, and then we're going to solder it. Now this might be a bit challenging. As you can see, the board is not screwed down yet. I haven't done that yet, but I have tucked these thick wires into this hole here for the drain connection. This is the source connection for the first MOSFET, and I did the same. It's a bit difficult, but I'll try to show you. I did the same here. There we go. There is the drain connection there and the source there. I've just put it through the holes for now. I didn't solder it yet. Sorry for the shaky image. Here you can see the wire sticking through already, and the same here. There are my wires, and what we have to do at one point is solder them and then cut them off because they're too long. What I will do first though is put the screws in there, so that the wires have the exact correct position, because without the screws might have to move around a little bit still. And once that's done, we will solder the remaining wiring here, and we'll get to that. But I'm gonna do the thick wires now after I screwed the board in place. Well, we're actually almost done. I did solder the 12 volt black wire on the bottom. As you see, the thick wires are in place and cut to the right length and soldered. We're now going to do the wiring that is still loose here. Solder these yellow, white and gray ones back to the terminal block, and solder the brown one and the red one on the board. And this is the two brown wires for the high voltage choke, which goes to these two pins here. Once we have done all that, we're basically done, and then we'll do a quick test for the unit. One thing I need to mention about the bolting it down: don't tighten the screw before all the others are in, because these frames are welded and they're not 100% exactly to measurement, I noticed. So you might have to seek the board a little bit. So what you do is you put all 6 screws in, you don't tighten them, so you have some wiggle room to seek, because the holes are of course bigger than the screw itself, and that allows you to compensate for the poor welding that Collins did. So then you tighten them when they're all in there, all 6 of them. Then you tighten them, and then you should be good. Well, it's done. As you can see, the last wires were also put in place. Now, we did use shrink sleeve. Remember, you need to have that. I don't recommend you do this without it. So these three wires that I reconnected are really done with the shrink sleeve to make sure you don't get a short to the chassis there. And we soldered the last wires here. The brown wires that go to the high voltage choke, and that's basically it. Now what I always do is I clean my solder work with lacquer thinner and a Q-tip, so you don't see all that flux residue, which makes it look unprofessional. Don't forget, this is a Collins piece of equipment. We don't want it to look like a homebrew project. It needs to look professional, like it just came out of the Collins factory. And this board does that for you. The professional design that brings back your MP1 to life better than it was before. Better efficiency, better reliability. So what we will do now is the last thing is to test it with a load, and I only do that to make sure that the unit works. You should not test it like that. Like I have said earlier, you should not run this thing with the cover not there, because the 800 volt really can kill you, so you got to be very careful with that. Once you turn it off, there is bleeder resistance there, and you need to let that bleed off for about probably half a minute. Alright, then you should be safe, but don't run this thing with the cover off. I will do it now because I need to do a test if it works. You should just test it by connecting it to your KWM2 or 1, and then it either works or it doesn't. Now the boards are all tested before we send them out, so that shouldn't be a problem. If there is a problem, you might have made a mistake with the wiring, so double check everything that you do. And of course there is always the slight possibility that there is a problem with the transformer. Although I have done many modifications, many retrofits like I showed you, and I've never run into a bad transformer, so that is very unlikely. But if you want to be absolutely sure, you can also do some measurements with your ohm meter before you start doing the work. But like I said, that is unlikely. And as you will see, the unit will work just fine. But again, be always careful with the high voltage that's being generated here, because it is lethal and you should be very careful not to touch it. So we're testing the early model after the retrofit. How did we hook it up? We have plus terminal here on what's called the hot terminal. This is the ground, so we're running it at negative ground. We're using an Alinco power supply Thing is capable of 32 amps, can measure volts as well as current. 13.8 volts. We probably lose a little bit over these cables here. They're not especially thick, but it's just a test. We're loading the 260 volt output with 2 incandescent light bulbs in series, and total power that we will be supplying to those is about 100 watts. Now the 260 volt output is specified for 55 watts, but I've noticed it can handle the 100 watts without a problem. We're not loading the 800 volts at all. I have nothing other than a KWM 2A that can handle that, so we'll leave that for now. It suffices just to measure the voltage. If that's there, then things are okay, if the rest is running. Okay, so we can turn it on by grounding this yellow wire. That's terminal number 3. When you pull that to ground, then the relay will power up, the internal relay. You can see the yellow wire actually terminating on it. And that will turn the whole thing on. Now remember, this is microprocessor controlled. It's not like the old unit anymore. What will happen is it will wait 2 seconds when I turn it on. That will give the filaments in the KWM radio a chance to taper off the initial current, because those tubes behave like PTC resistors. So the inrush current on tubes is quite high. After 2 seconds that is significantly lower. Then the HT will kick in, and that is less of a power shock on this unit here. Because I noticed when I do that with the old original MP1, then this thing goes into foldback, and the 32 amps is not enough to start it up. So with this microprocessor controlled delay, we won't have that problem. The other thing that the microprocessor does is a ramp up in pulse width modulation. So it doesn't immediately generate the highest possible voltage, it slowly ramps that up. And that also will help in capacitor life, and also for the transceiver it's a lot better. So enough talk, let's turn it on. Well, you saw the weight. Unfortunately the camera doesn't like the light from the bulbs much. If you listen carefully, you might be able to hear the 1600 Hertz whine. It's very low. And the current we're drawing is about about 9 amps, I would say. 9 amps we're drawing right now. So times 12 volts, 13.8 volts, a little bit more than 100 watt. The tubes take about, the bulbs consume 100 watts. I measured that before. So their efficiency, I did a calculation on this, is about 82% right now. 82% efficiency, conversion efficiency. When I did the same test with the old one before modification, I came to 69%. So we have 13% points increase in efficiency, which is quite good. As you can see, the MOSFETs are not heat sinked, and they don't get hot either. So this works quite well. Actually, I think I said that in the other video, this works so well that you can use this as your permanent power supply for your KWM radio, because it doesn't get hot. So you save the 516 F2 or whatever it is, and you can run your radio continuously from just DC. This one is much more compact than the 516F, and it is also a lot smaller and a lot less heat being developed. So as you see, it works well. We'll hook up a voltmeter so you can actually see the voltages that are being generated. Let's first turn it off again, and then we'll do that part. Voltmeter, let's turn it on again, and there we go. This is the minus 90. Remember, there is a pot, you can set it from 40 to 80 or something. It was still set for 66, which is usually the right voltage for minus 66 is a good voltage to start. But ultimately you want to set that potentiometer by observing the current through the PA in idle. I think the manual would say it, but I think it's about 10 or 20 milliamps, I'm not quite sure. Alright, this is the voltage that we have right now, the loaded voltage on the 260 volt output, 256 loaded with 100 watt. Like I said, your radio will not load it with more than 25-30 watts, so then it should easily reach the 260. This is a little bit tricky here, 800, you gotta be careful, remember what I told you. Right now we have 878 volts unloaded, so that's more than enough for your PA. But I would like to stress, you should not do this test. It is not good to run this thing when it's open. I'm doing this just to make sure that everything works after modification, and I don't have to hook up any radios. And that's why I'm using these incandescent light bulbs. But you should not do this. You should put the radio on this unit and then close the cover. The voltage that goes in here right now is 13.12, so that's actually on the low side. That is the DC voltage that we're putting in. As you can see, it all works fine. We're gonna close it up and it's ready to go. Here we have the late model. As you can see, there are no chokes there. And I'll show you the difference when you mount the board, the new board. There is really not that much of a difference. We got the same situation here. We got the red wires for the 800 volt AC. We got the orange wires for the 260 volt AC. We got this black wire here that is close to the red ones. This is the 800 volts being soldered from above. This is different. The 260 volt gray wire here does not go through the hole, but will solder on the board. I'll show you that. And here are the two other gray wires that go to this L3 choke. That is basically different because, like I said, you know, in the old one we went from here to that chassis mounted choke. That is not here. This choke will now be on the board. But again, like I said, I'll show you how to deal with that. I will not go through every step soldering this. I'll just show you the step where the gray wires are being dealt with. As you can see, I already soldered the red wires, the black wire here, the orange wires, the white one and the yellow one have been tucked through this hole. We are now gonna connect the gray wires I was talking about. We have gray wire 1 and 2. This one here goes to L3 terminal 1. This one here goes to L3 terminal 2. If you want, you can use an ohmmeter just to make sure. And that goes to, if we can focus, that goes to L3 1. You see, that's the one I just pointed out, goes to here. And L3 terminal 2 goes to here, and for the rest it's the same thing. The wires that come from the top is this brown wire. We have the black wire, which is the ground one. We have the other black wire, which is the ground one for the minus 90 volt winding on the transformer. That's actually this one here. T1 goes to pin terminal 9 of the transformer. This is terminal block 1, terminal 4. That's this gray wire here, will go there. And of course we have our 800 volts, which goes to here. And then we obviously have to do our high current wires for the MOSFETs, power MOSFETs. That is already stripped and ready to be put in there. There is the drain one, here's the source one. There is the other drain one, here's the source one. And here we have that 13.6 volt wire to supply the microprocessor, which goes on terminals 14 and 13 of the transformer, remember? And that will solder to this point like we discussed before. And there is no soldering to do here. We have the resistor there. So there is no brown wires to solder like we had with the early model. And the other choke that's missing is the 260 volt choke, the output choke, and that's actually already on the board. And that's all there is to it. So we're going to solder that now, and then we'll screw down the board and we're basically done. Well, the unit is finished, the late model. Remember, late model, no chokes there. We hooked up all the wiring, the brown wire is there. Remember the gray wire that goes to terminal block 1 number 4 goes to here. That is the difference with the early model, because we're now using this choke here that's on the board. And for the rest it's pretty much the same as what you did for the early model. This is the 800 volt. All the bottom wires have been soldered. The terminal block wires have been soldered. This is the 13.6 volt that's passed through to the transceiver through the relay. This is the relay control wire. I used a shrink sleeve there. For the rest I used the original sleeves. They were still good. This is the 260 volts and this is the -90. One thing I did notice when I soldered the thick wires, remember the thick wires, that went a little bit harder with this particular unit because the wires needed better flux. So I did use my water soluble flux, which seems to be more aggressive in terms of solder capability. It's the stuff I mentioned to you before. When I used that, it soldered just fine. Same here. That requires cleaning afterwards though, but you can just clean it with some water, hence the name. And that worked well. And of course there is this last little black wire from underneath to connect. Don't forget that, otherwise the unit won't work. That is an important one as well. And once you have done all that, then the unit is done, is completed. And we'll test this as well with the 100 watt light bulbs. We are ready to test the second unit, the late model. It's the same hookup as what we had before. 13.6 volts here and here. This is ground, this is plus. Make sure the jumper's in a vertical position. Remember, we have our Linko hooked up at 13.6, 13.8, and we have our voltmeter, which will check the voltages to make sure they are all there. First thing we're going to do is turn it on. Remember, by pulling this to ground, the on-off relay will be powered, and then the thing will start to run after 2 seconds. And there we are, after the 2-second wait and the slow ramp up. Let's first test the 260. We are at 260 exact, 260.9 loaded. Let's test our minus voltage, minus 62.9. Remember, you can set that with this potentiometer here. And then we're going to check our 800, which is unloaded right now. And we are at 796 unloaded. Well, you know, it is loaded, the power supply, but not the 800 volt. So all the voltages are there. What kind of current are we drawing? We are drawing 8.5 amps at 13.8 volt. And that corresponds to, if you do the math, to about 82% efficiency with this 100 watt load from these light bulbs, which is 13% points better than the original situation with the germanium transistors. So this concludes our instruction video for the RVB-MP1 modification / upgrade kit. Remember, when you assemble this and test it, do not test it like I did with the cover, you know, not there. The 800 volt and the 260 volts are enough to do serious harm to you, so you got to be really careful. Once you turn the unit off and you open it up, you got to give it about half a minute to let these high voltage capacitors bleed. There is bleeder resistors there like we discussed before. Once you have it bled, once you let it bleed off at about half a minute, you should be fine. Thank you for watching this.